Okay, everybody, so take a look at the worksheet that I just gave you. Do you remember what scatter plots even are?
No.
Oh.
Oh wait, what's the actual heck is that? Oh wait, oh you got it right.
Right, so a scatter plot, ladies and gentlemen. So a scatter plot is simply a type of graph that shows you each dot represents a separate data point. So for example, if I asked everybody in this room, if I said, okay, let's graph how old you are and how tall you are. I could each dot, like get those bits of information from each of you and then put it all on the same chart. And we would call that a scatter plot. And then as those dots sort of fall into line, or sometimes they fall into line, they have a correlation with each other, the two things that you're comparing, sometimes. So if I were to, maybe not just in this room, if I were, you know, I don't know, let's say I was a pediatrician, a child's doctor, wouldn't it be helpful for me to have an idea of roughly how tall children should be at different ages?
Yes.
Especially about how tall is a 5-year-old, about how tall is an 8-year-old. So that when my patients come in, I could see, okay, you're growing at a relatively, you know, I don't know, are you very tall for your age, very short for your age, stuff like that. So anyway, scatter plots can be super useful and helpful. So what we do is we plot all the data. We see if there is what we call a correlation. Do these two things have any relation to each other? And then we can graph a line or a curve if it's more of a, if it's not following in a straight line, sometimes it follows in a curve. We can plot a curve, but then we have an equation that models that data. So that's kind of the whole point here. So if we take a look at number 1, all we have to do is plot all of these data points. So they give you a graph. So let's all take a moment and just plot each of these numbers. So you're just going to do a dot at each one, right? So that's 2, 240. This one will be 4, 160. So we're just going to go ahead, take a moment. Yes.
Oh.
It's kind of, what's the word? Calming? I don't know.
No, this makes me anxious.
What?
That's
Oh, it's like cathartic.
No,
well, I'm also like really tired. So it's not really fun. It's okay though.
There. And you know what? Straight edge. We'll find out.
Wait, we have to take the next one. Like off.
No, so we'll talk about it. Just 1 second.
Draw a line through the middle.
Um,
Like, I don't know. Yeah.
oh yeah.
Just like that.
I want this. Yeah, same. My hair literally everything.
It's like this. Extra.
Oh, hang on to it.
No, this is the broken one.
Guys, who wants a broken pink?
All right, so once you have all of your data points plotted, is everybody listening? So you want to draw what we refer to as the best fit line or line of best fit. So a lot of times kids do this wrong. They just like connect the first and last dot. Your line's not necessarily going to go through every single point. You basically want to draw the line. This is what I imagine. I imagine the line is you and you're like a champion. And you know, when they run and they like high five all their fans, You know what I mean? Yes, you can imagine this. So you want to draw your path. These are all your fans. You want to be able to high five as many of them as you possibly can. So you kind of want to go right down the middle. I might do mine right about there. So you're not going to hit every single point. You're just going to get as close to as many of them as you possibly can. You have roughly half the points above, half the points below. Sometimes they all literally fall right on the line. That's great. Or, oh, you could think of this as bowling pins, if these are all the pins. So I guess I don't know enough about bowling. Sometimes you do special weird things to hit it the wrong way. You get what I mean? So obviously we're doing this by hand. Your line may not be perfect. We use computers to run the data and actually give us the exact line where it belongs. But, you know, this gives us the general idea. So now what our job is to come up with the equation of this line. I don't know where mine's going to hit the y-axis. So I don't have that bit of information. But what I can look for is I can look along my line and see if I have any good points where it crosses. Oh, here's a really good one on mine. It doesn't have to be at one of your data points. So right here, I'll put a red box around it. There's one pretty good point for me at 9,80. Your line might be a tiny bit different than mine though. So maybe you just got to look at your line and see if you can find a good spot where it crosses. And then I try and find a second one. Actually, this one up here is probably my next best one. So just pick your two best ones. If you don't have any that are perfect, get the ones that are as close to perfect. So find yourself, and again, it does not have to be one of the data points that you put down. It can be, but it doesn't have to be. So just look at your line for two nice lattice points. And everybody is probably going to have different answers here. So it depends on your line. We all drew it just a tiny bit differently, I'm sure. So once you have your two good points, whatever they may be, you want to figure out what those coordinates are. So for me, I have my first one at 2,240. And my second one happens to be at 9,80. And now, my friends, don't you know how to write the equation of the line if you have 2 points? You sure do. What do I need to find first? Slope. So I can kind of forget all of this and just use my 2 points, find my slope. So everybody go ahead and find your slope. Remember, it's y2 minus y1 over x2 minus x1. And you can go ahead and turn this into a decimal. I know normally we don't with slope, but for the best fit line, go ahead and make it a decimal. Oh, actually, I take that back. Well, let's do it as a decimal when we're totally done. So I have my slope. Well, no, well, I don't know. I guess it's up to you. I hesitate with changing it to a decimal before I'm done, because I don't want to use a rounded answer to figure out the rest of it. You know what I mean? So if I leave it as a fraction, it's going to be more accurate. But I also want to just make sure that we're all kind of in the same ballpark of each other. So if you turn this into a decimal, mine is negative 22.9. So grab a calculator and turn yours into a decimal. So I'll just put what mine is approximately, negative 22.9. We're not all going to get negative 22.9, but we should all be relatively close to each other. So if you have a slope that's way different than mine, that doesn't make sense. But maybe yours is like negative 23, or maybe yours is negative 21.
What about 26?
Whoa.
Is it negative?
Yeah.
That seems like what are other people getting? Are you getting kind of close?
I got negative.
I got,
Negative 25?
I got negative 20.
Negative 21.
Okay,
All right. So we're in the ballpark.
we're in the 20s.
Okay. So now I need to, of course, figure out my Y-intercept. I can't tell it from my graph. I don't know where it is. So I'm not going to use this rounded answer just because I don't want to use a rounded answer to get everything else. So I'm going to go back to my fraction. But I'll just use point slope form. And I'm going to use the 981 because it's smaller. And let's go ahead and turn this into standard form, not standard form, slope intercept, just so we can all see. We should all be in the same ballpark of a Y-intercept also. So go ahead, bless you. I'm going to clear my fractions because I don't want to deal with them. And now I'll go back into a decimal. I knew that was negative. Okay. So in the box here is mine. My slope is a negative 22.9. Again, yours is not going to be exactly the same, but roughly around that. And then my Y-intercept, I got it at a 285.7. If I look at my graph, although I can't see 285, it at least looks like it's a reasonable answer, right? I know it's certainly going to be something bigger than 240. So this is just going to keep going up. This is going to keep going over. So I know, like if I had gotten 1,000 as my Y-intercept, that doesn't make any sense, right? But if I'm in the, mid to upper 200s, and again, we're not going to be the same here because it depends on just how you, I don't know, just a tiny little difference in your line is going to give us a bit of a different Y-intercept. But we should all be in the same relative general area. Does that make sense? And are you getting values that are roughly in the mid to upper 200s? Yeah, so I'm thinking, I don't know, if you had like 250 to 300, somewhere in that range. Yeah, we're there? 313? And that could be reasonable. And you're,
like it'll make sense for my line, but like
yeah, so your line must just be steeper than mine.
definitely.
Yeah, okay. But that's really it to scatter plots. And now I can use this equation that I came up with to predict different things. I could say, okay, well, what would happen? I don't know what these are. It's just an X and a Y. But let's say if I wanted to know, hey, what would I expect my Y value to be when X is 11? When X is, and that's not even on my graph, but I can use it to predict these things. So that's exactly what pediatricians do, right? Well, just as an example. They have, my son has his appointment on Monday. I'll go and I'll find out based on, the general population of 5-year-olds, how tall is he? Is he extra tall, extra short? They do a head circumference. Did you know that? They measure around your head to see if your head is growing at the right rate. Very interesting stuff, but all of that is, they have created it using basically just data from thousands of children. So we sort of have a baseline to go off of. Does that make sense? All right. Now, oh, you know what we didn't talk about is the way that these data points are trending with each other. So I mentioned that there can be a correlation. And I do see a correlation. So a correlation just means that the data is tending to go one way or another, but they're all kind of going together. I don't have random data points all over that just looks like confetti. It looks like they are kind of going down together, right? This is what we refer to as a negative correlation. So as my X values are getting bigger, my Y values tend to get smaller. That is a negative correlation. I'll put this right here. Negative correlation. Okay, let's see. I want to do a positive correlation one. Would that be this one? Oh yeah, let's do number 2. Number 2 looks like it's going to be positive, so let's try it. So again, we get to have a little moment of zen here and just plot all of our data points. Now, again, we're doing this by hand, so they're not going to be perfect. I don't know exactly where 0.3 is, but I can estimate.
Okay.
Okay, does everybody have theirs plotted? So before we even draw our line, we might want to ask ourselves, does it look like the points are going in the same direction with each other? Yeah, it looks like they're going up together. So as my X values are increasing, it looks as though my Y values are increasing. Now, it's not quite as tight as the last one was. That refers to like how closely the data points fit to the best fit line. That's something called our R value. And ours is not going to be great here. That's something you would have to figure out on the calculator, but that's okay. So go ahead and draw your best fit line. So again, you want to try and get as close to as many points as you can. I think this looks pretty good for mine. And then I'm going to take a minute once I figure out mine. I'm going to pop it into the graphing calculator, and the graphing calculator will tell us what the real one is. So we'll see how close we get. All right, so once I draw my line, ooh, I've got a bunch of good points. So just look for two of yours. That one's perfect. And if you don't have any that are perfect, again, just go with the as close as you can get to being perfect. We're doing it by hand, so they're not all gonna, I think those are pretty good. So I'm gonna use the points 1/600. Oh, and can I just make one point? I think I don't think any of you are doing this, but I can't just look at this and say that my slope is, oh, well, aren't you just going up 2 over 2? So isn't your slope just 1 over 1? No, because my scales are completely different. So I don't just have a slope of 1 up 1 over 1. You get what I'm saying? I'm using completely different scales. So I really got to take my points and do it that way. Okay, so go ahead, find your slopes. And we'll see how close you get to the real deal once I pop it in the calculator. Gosh, I haven't done a scatter plot on a graphic calculator and I can't tell you how long. Oh, there we go. It's like, I feel like it's just like when you're trying to find like a setting on your phone and you just haven't gone there in a really long time. So you just gotta click around till you find it. Same idea. Okay. 1100, that would have changed everything. Okay, 1100. Okay, so here is my data points on the graphing calculator. Now I want the calculator to run the best fit line, so it'll run it perfectly. Now I just gotta remember how to do that. I think you do. Oh, yes, I did it. Okay, so there is the, there should be our slope exactly. It's 206.62. Mine was 200. How close did you get? Did you get somewhere in that region? Woo, 240. Can I do what? For your slope.
Oh, my slope?
Yes.
Oh, yeah.
So our slope, again, you know, you gotta use a grain of salt here. We're doing this by hand. It depends. I mean, you gotta, first of all, it depends how accurate did you plot your original data points. So if you're a little too willy-nilly, you're gonna have your data points slightly off, and then your best fit line would be slightly off, right? And then we're also eyeballing where we think about the middle is. So there's certainly a range of flexibility here. But it's just always fun. I like to see like how close did I get to the real deal. So 206.6 is the real slope. And then a Y value minus 400, they're getting 434.7. And let me see if I can remember how to make the best fit line graph with the data points. Oops. Oh, now you have to go over to here for something. Did I do it? Yes, I did it. Woo! So there's what it should have looked like officially. How interesting.
Oh, it's okay. It's like close.
Have fun, huh? Should we do one more? What's on the back? I feel like the back was different. Oh, yes, the back is a little bit different. So let's talk about, oh yeah, they're asking more. Let's do one more and then we'll look at the back. Because the back is different style question. So anybody have a favorite number, 3 or 4?
4.
4, all right, let's go for it. Interesting data points. Oh, glad you picked this one. Oh, and I just realized on the last one, we forgot to talk about what type of correlation we have. That's okay. We'll go back to it. All right. Did you come up with a graph that kind of looks like mine?
Yeah.
Yeah. So when you have these data points that are just sort of all over the place, does it look like the points are traveling up or down with each other? No. To me, it just looks like someone threw confetti in the air and it's just all over the place. So when there's no clear distinction, they're not clearly going up together, they're not clearly going down together, we say that they have no correlation. This would be like if I asked you, okay, let's make a scatter plot of how tall you are and the grade you got in your last test. Do you think they have anything to do with each other? No. So you would just see a bunch of random stuff that has no relationship to each other. That's what we expect to see when the data sets have no correlation. So rewind to number 2. This one, they are clearly going up together. We call this a positive correlation. And that, my friends, is everything you, so yeah, when there is no correlation, I don't draw a best fit line. Where would I even draw it? It's, doesn't make any sense here. There's nothing I can really do with that one. Okay, does that make sense? Yeah, we're good? Okay, on the back, let's take a look at what these are asking us. Number 5 says, by examining past tournaments, it's possible to calculate the probability that a school wins their first game in the National College Basketball Tournament. How interesting. Okay, so if we have the rank, here's the probability that they're going to win. Each school's rank going into the tournament is a strong indicator of their likelihood of winning their first game. This can be expressed as, and then they give us the function right here, where X is their rank out of 16, bless you, and Y is the percent chance they have of winning their first game. So what they have done is they have already taken that data and made a scatter plot of it for us. All right, great. So now we have to answer these questions. What does the Y-intercept of this function represent?
It would be the top pair.
Yeah, would be a 100% probability of winning that first game, right? If that's going to, you can't get higher than 100% probability. So 100% chance of winning first game. All right, and then B. So, oh yeah, and then Sam, you said top rank, right? So I'll leave it, we can add that too, because here we're really just talking about the y-axis, but there's your,
It would be like one and not like.
yeah, so it doesn't even really, yeah, because you first, we don't even, it would really be a 0 rank. So, which doesn't really exist, right? So nobody has a 100% chance of winning. All right, B, according to the model, a school ranked number 5 has what probability of winning their first game? So this is convenient because there is no 5th rank in the chart that they gave us, but by using our model, we can have a relatively good prediction. So if you are 5th rank, approximately what's your probability? Yeah, it looks like right about 70. If you went 71 or 2, I could see that also. I'm gonna go 71%. And I'll put the squiggle in front to say approximately, or somewhere right in that region. I have no idea if these are accurate. Angelina, tell us if this, do you feel like this holds water? Yeah, all right. I mean, it makes sense. The higher ranked you are, the better your chances are. Are we ranked? Is Tantascwa ranked?
We got it.
Alright.
We have a good basketball.
We-
team.
I would say.
Football though. Oh.
I will tell you, one of my favorite Tantascwa memories was whenever that was, gosh, probably 13, 14, 15 years ago, something like that. We were undefeated in boys basketball, undefeated the entire season. They won states and whatever. Then the second season, they went all the way, and then I think they lost the last game, the state championship or whatever. But it was super exciting because everybody was so excited. They had buses going to all the games, and everybody was we were so pumped. It was very exciting, and it was a lot of fun. Everybody was there. All the teachers were there. We went all over. We went to Worcester. Nobody ever does that. We don't go anywhere anymore. I mean, now I know it's COVID times, but so you're leading the Warriors to championship, right? Yes, bring it back because that was such a fun time. It was very exciting. Do any of you remember? You probably weren't even born yet. It was a long time ago. But maybe you have, did you know? Did you hear of this? I don't think yeah, I had not met my husband yet. I know that. Because I remember being single at the time. Because I remember I went with another girl that was working here. And we were complaining about men. I remember that. Yeah. Go so fast. But yeah, so I met my husband in 2010, so it was before that. So 2006 is too early though, because I didn't start here till 2000, maybe it was like 2007, 2008. Ah, yes. What? Yes, look down there, you'll see. And it was 2 years in a row. It was so cool and so fun. Anyway. All right. Let's try number 6. And then we are going to solve systems by graphing, which is nice and easy. All right, the cost of a flight related to the distance traveled. Oh, yes. All right, so they have already modeled it for us. They gave us an equation. X is the distance in miles and Y is the cost in dollars. Okay, so doesn't this make sense, right? The further you fly, the more money the trip is going to cost you, right? I don't think these dollar amounts are quite accurate because it costs an awful lot more money than $200 to go, what, 1,700 miles? I don't think so. But anyway, they do go up together, right? So you can imagine the further I'm going, the more money it's going to cost me in my plane fare. So what does the Y-intercept represent here? Exactly. And so think about it, even if I'm not flying very far at all, right? Before I even step onto the plane, aren't there fees? There's all sorts of fees.
Plane ticket.
Plane, yeah, just the processing fee, the baggage fee, all the fees, right? Before you've even gone anywhere, there's still all these fees. So that's going to be representative on my Y-intercept. So we'll just call that baseline fees. So if you want to even list a few, tax, I don't know, service fee, you know, all those fees that they charge you. Oh, sure, parking. Actually, I don't know. Well, I don't know. Would you lump it? It's certainly part of your cost if you're going to go take a flight. But I'm not paying my parking fee to the airline. All right. Anyway, using this model, what would be the cost of a flight that travels 1,100 miles? Round your answer to the nearest dollar. So we can kind of guess it from the graph, or you could take 1,100 and plug it directly into your formula for X, right? I'll actually do both because I want to see how accurate of a guess I get from my 1,100. Ah, yeah. Because really, I'm not totally sure where 1,100 is. So I'm going to guess it's right around, oh gosh, maybe 130.
Sure.
But I want to plug into the formula and see and get a more accurate answer. So I would be doing 0.0901 times 1,100 plus 31.4. Let's see what that gives us. $130.51. Wow. $131. Oh, $30.51. So quite accurate, just based off of my guessing. All right, easy peasy. On your test, which I just made yesterday, there is one problem where I have you do basically everything that we did on the front. So you're going to plot the points. You're going to draw your best fit line. I do ask you to tell me if it's positive, negative, or no correlation at all. And then I do ask you to write your equation in slope-intercept form. So you could certainly start in point slope and then rewrite it. And of course, I'm going to give you a window. So, you know, I'll have some flexibility with these numbers, but they should be in a, you know, relatively reasonable ballpark based on your graph.
When did you do the test?
The test is on Thursday. this coming Thursday.
Wait, is today Friday?
Today is Friday.
Thank
I
God.
believe that is the 17th. And that's on purpose. I don't know if we're gonna have any snow days next week. I mean, I never know, but
We probably should.
there was some weather on Friday, but I think it kind of just disintegrated into rain now.
Well, it's like 50 degrees outside.
February is traditionally the snowiest month. Well, not recently, but in New England anyway. Let's see. Oh, that's interesting. There was supposed to be snow this Sunday and it's gone. All right, so Thursday, Friday next week, it's very rainy, but yeah, it's gonna be in the 50s. So probably gonna stay as rain. But if somehow we get a cold front in there, that's why I wanted to make sure that I had the test Thursday, so we had a buffer day. But anyway, assuming we have all of our days next week, I have D Block is going to do some students there wanted to do a presentation on NFTs. It's a non-fungible token. So if any of you wanted to do a presentation of some sort on Friday, assuming that we didn't have a snow day.
That takes extra work.
Wait, I don't know. if
I agree. I did say that I would give them extra credit. How much extra credit was not negotiated.
On anything?
Permanent 100 at the class.
Yeah, that's not gonna happen,
Wait,
but,
anything? Like anything?
well, I'm super interested in NFTs and somehow we got to talking about it. And then they were like, would you give us extra credit if we made a presentation? I'm like, yeah, okay. All right, let's solve systems by graphing. Let me give you these.
I agree.
I mean.
5, there you are. 1, 2. There you are. 1 and 2.
I think. The JV's at 1:30. Yeah, I don't know. What?
You're welcome. Okay, everybody. So solving systems by graphing is literally the easiest way because you already know how to do it. You already know. Let me just, I'm looking at those. No, it's all right. All right, we'll just start with the first one. So if I want to solve a system by graphing, I literally just have to graph both lines on the same coordinate plane. Wherever they cross, that's my answer. That's it. So if you can graph a line, you can solve the system by graphing. So for my top one, that is not in any kind of form. So you know what I'm gonna do? I can get that in standard form real easy if I just add that 9 over and flop it around. So I might do this. I think this might be fastest, right? If I just add the 9 to the other side. Isn't that thing in standard form now? Now it's pretty fast to graph in standard form because this number divides into this one easily.
The parallel.
They are? Oh,
Yeah.
funny. How are you guys so fast? Well, anyway, let me graph this one. So that would be at y is a -3. Sorry, the line is a little light, but hopefully you can still see it. The x doesn't go. I mean, it's not that bad. It's only a -4.5, but I can always just do my slope. -a over b. So -2/3. You still have your straight edge, so you could draw them using your line here. There's my first one. And then I just graph my second one. Oh, I'll get that one in standard form also. So if I just minus the 3y to the other side. I'm gonna divide everything by -1 because it bothers me that they're all negative. Oh, and this one's actually super easy because both of these numbers divide into 6. So that means y is just gonna be 2. And x is just gonna be 3. So yes, oh, how interesting. These two lines are parallel. So where do they intersect?
Never.
They don't ever. So what's the solution? There isn't one. Correct. So no solution. And I'll add because the lines never intersect. So yes, that can happen, obviously, it just is. My lines are never going to intersect, but that's okay. We'll try number 2, see what happens. That one's almost in slope intercept form. I'll just put the -2x first. That one's going to start at a +4, and then I just follow that slope. I like to go, when I'm solving systems by graphing, I like to do extra dots because it's likely that they're going to cross at one of the dots. I don't know. So that's what I do. But you do you. The second one is in standard form. Y is going to be a -1. And I'll just follow my slope. -9 over -3. Get a +3. Ah, ding, ding, ding. Look right there. They're going to cross right at that dot right there. Did yours cross where mine crossed? And so, but that's not the answer. You have to then tell me what that ordered pair is. So this solution would be at 1, 2. About what?
For today.
What about for today?
For appointment for today.
Oh, wow.
Or just the
Yeah.
other one will be next week.
What other one?
That's that one.
Oh,
So I told her
oh, so what time are you going?
3:40.
Oh, okay. Yay.
I'll tell you.
Yeah. Oh, I'm so happy.
Okay.
All right, so 1, 2. By the way, ladies and gentlemen, you could always take your solution and you can plug it back into the original and it should work in both. So if you just want to double check, if you're like, well, what if I just graphed this wrong? You can take 1, 2 and make sure that it just pop it into each one and should work out just fine. And it does. So yay, there's my solution to that one. See how easy it can be? So if you graph a line, you can solve a system. Now, are there limitations to solving by graphing? Of course there are. Because what happens when the solution is not at a nice lattice point like 1, 2? What if it's really at 1.1, 2.7? You think you're going to find that on a graph? No. So if it doesn't cross at a nice lattice point, solving by graphing, especially by hand, is not really useful. Okay, but it is nice to know, especially because you already have the skills, you just put them together. All right, any questions? No? Oh, we got 25-ish minutes. So could you try? Let me see, is there one? I do want to do one where. Oh, has anybody come across one where? Well, I don't want to give it all away. Number 3 looks promising. Oh yeah, number 3. Can we do number 3 together? It's almost as if when I created this worksheet, I went in a certain order. Go figure. Thank you, past me. All right, why don't I try number 3? The top one is almost in slope intercept. I just got to get rid of that -y. So let's divide everybody by -1. And I'd get +x + 4.
Oh, it's the same one.
Downstairs, let's see, if I do the same thing, I would minus the 4 over, divide everybody. Well, isn't that interesting? I end up getting the exact same line for both of them. Correct. Now, oh, I want to make a very clear distinction though. So if I graph the top one, I mean, once you realize that they're the exact same thing, you don't have to actually graph them because you know what it's going to look like. But I just want to show you. So there's my first function, and then I'll graph my next one. I'll use this orange color. I mean, it's literally the exact same graph on top of each other. Sometimes kids make the mistake of saying that the answer to this is all real numbers. That's not true. That is not true. Is this point right here, I don't know, 2, 1, is that a solution to that system? Is that a point on that line? No, but those are real numbers. So you can't say all real numbers here because that's not true. What is true is that there are infinite solutions. You're never going to run out of solutions because remember, the solutions are where they cross, and they cross everywhere on this line. But they're not crossing at every number that exists, right? They don't cross here at 3, 1. They don't cross at, I don't know, -1, -2. There's lots of numbers where they don't cross, so you can't say all reals, but you can say infinite solutions. Does that make sense? There's a big difference between the two. I know Jeff Bezos has like basically an infinite amount of money, right? I don't even think he could spend it all if he tried. Does he have every single dollar bill? I have a couple of them in my pocket, well, not in my purse. Not many, but he doesn't have every single dollar that exists. But he does have an infinite amount of money. You see the difference? Same idea here. So we're saying infinite solutions. Does that make sense? Yeah. I feel like I say that a lot. That makes sense. That makes sense. Catchphrases. I should get a soundboard. Anyway, questions? No? Easy? Easy peasy. That's another one. Lemon squeezy. All right. Okay. So anyway, that's it. If you could just try, you can probably finish before back and forth. Just get as far as you can, and that'll be it until Monday.